All right, seems like a good time to get started now. So a brief introduction to myself. I'm Baron Schwartz, the CEO and founder of Vivid Cortex. My contact information on the screen. Always enjoy hearing from people, so please feel free to email me or tweet to me at any time. You can also connect to me on LinkedIn. However you find me, I'm happy if you have any questions that I can answer or advice that I can give or any way that I can be useful. During this webinar, you can tweet questions with hashtag VividCortex at any time, and I will try and answer them as I see them. And afterwards, this webinar will be recorded, and the recording will be available on YouTube, and we will post a link and a blog post on all of our social media and on our blog with the slides and the video embedded. So with no further ado, let's go ahead and get started. What I'd like to talk with you about today is about reducing database total cost of ownership. This is something that I have quite a bit of experience doing as a consultant in my previous life. Prior to founding Vivid Cortex, I helped a lot of people drive down database costs. And one of the things I noticed was that there are particular repeating things that come up. A lot of those are technology related, and a lot of them are more business and more team oriented. And so I wanted to cover a few of those categories of sort of the low-hanging fruit, the biggest, most common problems, and how we can find some solution to those. And everybody needs a list with a particular number of items. So I have a list of 5 items of key areas where we can look to try and find those costs and how to reduce them. So the first question to ask is whether your databases are too costly. Are you spending more on your database infrastructure overall than you could be? Not necessarily more than you should, because should is kind of a relative term, but more than you could be. And you might be spending more than you could if you've over-provisioned your databases and you're using too much horsepower for too little work. And if you're not sure about that, then that's actually one of the common problems that I've faced in the past. People express that in different ways. They would say things like, I'm not sure if I have enough capacity for the holiday season, or I'm not sure, could I downsize my databases and still provide as good quality of service? Another common way to express this is that people would say, you know, my databases are growing, they're growing by various metrics such as load or queries per second or the amount of data that I store in them. And I want to know how much runway I have left before we run out of capacity and, you know, it becomes a crisis kind of situation. So if any of those things are questions for you, then it might be a sign that you could look a little deeper. You know, you may be fine, you may not be spending more than you could, or on the other hand, you might have some opportunities to reduce your cost. Another common thing that people would tell me is, you know, we're a fast-moving team of primarily developers. We don't really have a database expert on the team, or the person who's a database expert on the team is overloaded. And every time a database performance issue comes up, it's easier to just buy a larger instance of database server on AWS than it is to try and fix those problems. So people are trading off one thing for another. They know they're spending more than they potentially could. They're not sure necessarily how much they could save, but they know that they're just throwing hardware at the problem. The next couple of reasons that I've seen are a little bit harder for people to understand because they can be hidden. They're a little bit less obvious than sort of knowing that you're throwing hardware at the problem. And one of those is being unaware of the workload that the application is really throwing at the database. And in a lot of cases, that workload won't show up in things like a slow query log. It won't show up in application performance management tools. It's pretty invisible, but yet it constitutes a lot of work on the databases and can cause a lot of additional latency and network traffic and so forth for the application. And then the final thing is buying fixed resources such as renting a specific instance size in AWS's EC2 cloud for a workload that varies heavily. And this is much more of a niche case, as we'll discuss a little bit later. But if any of these sound like they might be relevant for you, then there might be an opportunity to drive down the cost of your databases overall. So how we know this, there's kind of two ways that we can know whether you're spending more than you could be on your database. One is you already know. And a lot of people have come to me already knowing. As I mentioned, we know we're throwing hardware at it to solve the problems, but that's the best that we can manage right now. And then the other case is you're not sure whether you know. And in that case, you need to measure and find out. And then the big question becomes what to measure. So we'll dig into that a little bit as well. So let's look at what actually drives costs in the database. And this starts from sort of the very obvious and goes towards the much less obvious. So the most obvious thing is the cost of servers, whether you're purchasing them or renting capacity from a cloud computing provider. If you're purchasing them yourself, or if you are hosting in, let's say, a colo like Rackspace or something like that, you know the cost of your servers, you know the cost of your power space and cooling. The next thing is the team of people who are running those servers. And typically that's one or more database administrator and probably some fractional amount of other resources. It could be system administrators or even developers in-house who lend a hand with the database part-time. And you may or may not be actually accounting that in your books towards the cost of the database, but people are usually quite aware that that goes towards their database cost overall. And then there's also outsourced services such as Percona and Pythian and then the like, fractional resources that you're using on your databases. There are a handful of other things, but generally, the people and staffing costs most of the time pretty transparent to an organization. Where it gets a little bit less obvious is in the developer productivity side of the equation. This is one of the costs that's often completely invisible, doesn't really occur to people. It would be very hard to quantify if they did think about it. But developer productivity is a really big deal. And just to slide in a little bit of a plug here for Vivid Cortex, since I didn't really talk much about Vivid Cortex per se, our biggest successes with customers are where we make their developers much more productive. It's not really about making the databases more productive or one or two database administrators more productive. It's really about empowering 10, 50, 200 developers to move much faster. And that feeds directly into bullet point number 5, which is about IT's ability to deliver. If you ask any CIO, CTO, VP of engineering, or even CEO of a technology-focused company what their biggest problem is, what is the number one thing that they wish they could really move, it would be, and this comes out in survey after survey, that IT fails to deliver projects on time, under budget, and with the required functionality, security, and other technical capabilities. And so that's really at the root of what drives cost for the organization overall. If IT can't deliver things on time, under budget, and with required functionality, then you have a much larger problem than the databases. And databases play a key bottlenecking factor in that whole equation. And we can dig into that some other time, but I did just want to mention it now. I generally see 5 opportunities for reducing costs in your databases. And these come through query efficiency, reducing the diversity of the databases that you're running in your application stack, consolidating servers together and making sure that your servers are the right size, and sometimes cloud computing, and maybe not for the reasons that you think. And so that's today's agenda. We're going to dig into each of these in detail and see how each of these might apply to an organization. And I'm going to use Vivid Cortex as an example in many of these, because I've applied a lot of this thinking to how we've architected both our business and our technical systems here. So category number 1 is query efficiency. And it's really about query inefficiency. You can only drive so much efficiency out of queries. But there's a lot of inefficiency that can be created. And so it's not necessarily focusing on the good so much as eliminating the bad. I like to be a positive thinker, but in this case, you got to be thinking about double negatives. So if your queries are inefficient, or if your application is querying your database in an inefficient way, then you're wasting a lot of database resources and you're causing poor performance for your end users. And this is most relevant for databases that are fronting some kind of a user visible or customer visible application, where slowness or unavailability on the database backend directly translates to unavailability of functionality or even downtime overall for the end users. There's a few key causes of query inefficiency, and I have given a couple of webinars and written some ebooks about this, and I'll have some links to those resources at the end, but I just wanted to go over a few of those categories here, the biggest offenders. And the biggest offender by far is using no indexes or poor indexing. The query efficiency is really, in fact, all efficiency, all optimization is really about cutting out useless things. It's about eliminating, trimming anything that doesn't produce results for you. And there's a few different ways that might be happening in a query. One is that you're looking at too much data. That can be looking at too many columns. It can be looking at too many rows. Looking at too many rows in a table for a query is by far the most common problem. And the solution to that is almost always an index which identifies the few selected rows that you're interested in. There's also a variety of ways that poor indexing could be defeating query performance and causing a lot of inefficiency. And those come into play usually with more complicated queries such as group bys, sorts, group by and sort on different criteria, scanning and sorting, and then sorting again, and top end limiting the results, kinds of things. The next big offender is a query pattern that's driven by the application. From the database's point of view, each query actually can look very efficient, but taken overall, you can see that there's a lot of wasted work. And we call that the N+1 query pattern, and it usually starts from some parent object and drills down into a child object, and there's a many-to-one relationship. So for example, you will have the N+1 be N queries for a user's social media updates, and the 1 is the query for retrieving the user's social media profile. So first you'll fetch the profile, and then you will fetch every one of the user's social media updates. And you'll do them one at a time. And you could do that in a join, or you could do it in a bulk query, where you retrieve all of the rows with a single query, whether that's just with a simple where clause or with a where clause that has a comma-separated in list. But the bad query pattern here is driven by application code, such as an inefficient Ruby gem. This often happens in Ruby on Rails apps. I don't want to cast stones at any particular one, but people in the Rails community understand when people say the N+1 query pattern, it's actually a terminology of the trade there. The next one is wasteful use of prepared statements. And prepared statements are designed to be reused for efficiency, and if they're not reused, then that efficiency is lost. And it's additional load everywhere and additional latency everywhere. And finally, long-running transactions. This is something that's probably not going to come up on a lot of people's top list, but when I dug through all of my notes and a whole bunch of material that I had written in the past on these types of topics, it stuck out to me. This was actually something that kind of surprised me a little bit to remember as I was preparing for this webinar. It stuck out to me that a lot of problems come from transactions that open and do some work and then they don't commit. And they may commit because somebody forgot to commit. They may fail to commit because the application code is doing some thinking, or it's waiting for something else to finish. But in any case, a transaction that opens, does some work, and then stays idle for a long time without committing is a big problem for the database. The problem is that transactions in ACID-compliant databases need to create a consistent view, usually for other transactions that are running, as well as for the transaction that's open. And the way that they do that is either through locks or through keeping old historical versions of rows as the database updates. And in both cases, you're essentially preventing other things from doing their work. In the case of locks, you're holding exclusive locks on rows and preventing other transactions from modifying those rows. And in the case of old historical row versions that are used to create a consistent snapshot of the database as it existed at the time the transaction opened, you're keeping a history list of old rows around and preventing those from being purged once they're no longer visible. Now, once this old long-running transaction commits, the database can come in, remove old row versions. That's called different things in different systems. It's called vacuum, for example, in Postgres. But while that transaction is open, that process is blocked and things get slow and bloated. And they get slow for a lot of different reasons. And generally, these databases assume, optimistically, that transactions are short-lived and they commit quickly, and so they're optimized for that scenario and not optimized for growing very large history lists. And in the case of, I can speak most authoritatively about InnoDB. When InnoDB's history list grows long, it's actually extremely inefficient. So that's a big problem. Now, a couple of these can be measured. And some of them we have support for in Vivid Cortex, and so I'm going to show you some examples of those. The first thing that I mentioned, the biggest offender, is poor index usage. And there's a few different ways that you can measure index usage on a query basis, and that's really what you need to do. You can't look at index usage overall for the whole server. You can't look at global averages. Those global averages will present misleading pictures to you, where you might think that things are fine, when in fact there's a small proportion of the query workload that is performing extremely poorly indeed. So you need to drill down at an index level and at a query level to really see this. So the most helpful thing is if the database server itself provides instrumentation for how queries use indexes. And you can see this in Postgres with the various relation views. You can see it in MySQL either in some community extensions like the user statistics extension that Google contributed and has been maintained by Percona and Facebook and others, which provides index and table statistics. You can also see it in newer versions of MySQL in the performance schema. In some products, you can't see this kind of information. In some products also, it doesn't really apply. For example, Redis doesn't have a concept of an index. And in some databases like MySQL, you can actually see little flags set in the protocol on the wire. That's one of the things that Vivid Cortex does. We decode that protocol coming back across the network, and we can pull out those little flags and say, this query didn't use a good index. Failing all of those kinds of built-in instrumentation, you need a tool that's going to take examples of those queries and run explain plans on them, analyze the explain plans, and then show you which ones are not using indexes according to explain's output. And that's something we're building support for in Vivid Cortex. We don't have that yet. We do capture explain plans of running queries, but we don't yet analyze that for you and draw your attention to the ones that are missing indexes. There's a really popular thing in the MySQL community that kind of came from some information that's written into the MySQL slow query log. There's a couple of metrics that are in the header of every query in that slow query log. There's the rows read and the rows returned. And there's kind of a popular cargo cult rule of thumb, I guess I would call it, about this index ratio, the ratio of rows read to the rows returned by the query. And although sometimes this can highlight queries that are not accessing indexes correctly, it also highlights a lot of queries that are perfectly well written and just happen to return very few rows. For example, queries like a group by that will operate over a lot of rows and return only a few. So in my opinion, that's one of those things that's right except for the times that it's wrong, and so you shouldn't count on it. A couple of screenshots of how you can see this in Vivid Cortex. One is that you can rank the queries by missing indexes in the top queries tool. So you flip into the highlight, navigate into the top queries tool on the left navigation, and then you select to rank queries by missing indexes in the drop downs at the top. And you'll see that sometimes there are queries that are not going to use an index period. You know, they're just system queries over system status views and things like that. And then you'll also see the query that I've highlighted with the red oval in the bottom, where we have a subquery. And it's selecting a distinct set of columns from a subquery. It turns out if you look at the whole query there, that's a materialized view in that subquery. And that view is not indexed. So those are some of the places where, for example, I think we can factor this query out. We'll take a look at it. It's not a big time consumer. You can see the popover on the bottom right where I'm hovering the mouse over that query's time column. And you can see it's a very small fraction of the total server workload on this server. So it's not as though it's a big consumer of resources overall on this server, but it still might be worth looking at in order to improve some application response time. Another feature inside of Vivid Cortex that we can look at is the prepared statement statistics. So if you drill into one of those queries, I selected one that's a prepared statement, which we can measure and analyze because we're seeing that on the wire. If you drill into that, and then in the drop-down menu that I've highlighted with the red oval, you select to rank the metrics in the chart by the count, then we break out the constituent parts of that query's behavior. And in this case, the close, prepare, and execute actions on this query for a prepared statement are all separately highlighted. And you can see that about a third of the time is spent in prepare, a third of the count is spent in prepare, a third of the count in execute, and a third in close. And that's consistent over the lifetime of this query. So this is a prepared statement that we're not using efficiently. If you're only going to use a prepared statement once, then the only potential benefit of doing that is possibly for security, just to make sure that parameters are escaped and you don't get a SQL injection attack. Now, we have frameworks in our own code base that we can use to do this more efficiently and still avoid any problems with security, any implications of SQL injection attacks, and so forth. So this is not a particularly huge win in this exact example, but we have had examples in the past where we've significantly improved things by taking heavy queries that were doing a 1 + 1 + 1 pattern of prepare, execute, and close, and not reusing that prepared statement. And we either reused the prepared statement inside of a loop, or we got rid of it and we just sent a query as a one-off. So those are a couple of examples of what it looks like when a query is being wasteful. And a couple of links. Again, these slides are going to be posted online. The next category of potential efficiency that we can drive is by reducing database diversity. And by database diversity, I mean using too many different kinds of databases. There's a trend that I call polyglot persistence. I don't know of a better term for that. Database heterogeneity. They're all a mouthful, whichever term you want to use. Maybe database diversity is a better term. But there's a trend towards using the right tool for the job with air quotes around it. And although that's great in particular cases where you have a use case that doesn't suit well in a particular database, for example, we use both MySQL and Redis in our own backend. It can be, you can go overboard with that. And developers can introduce a database and just start using it when you might actually be able to get away with using another database instead. Now, there's a trade-off, a balance between these things. You know, a database like Elasticsearch is really, really good at search, and relational databases can be okay, but generally not really, really, really good at it. Similarly, a relational database with JSON functions, for example, the more recent releases of Postgres have built-in JSON data types and JSON functions and so forth. They can be pretty good at document-oriented workloads. But are they really, really good? You know, are the drivers optimized? Are the code paths optimized for developer productivity and so forth? Oftentimes not. So developers will turn to something like MongoDB or Couchbase or what have you. And that can turn into too much database diversity if you're not careful. And the cost that comes out of that is things like training, knowledge sharing, hiring people to administer these things. You know, what you'll often end up with is a database that only 1 or 2 people really know well, and other people are just sort of hoping that things keep going okay. You know, I hope that we don't have an outage when John is on vacation, because John's the only one who knows how to really love and care for that database properly. So those are risks that accumulate as well as costs, because if John is the only one who knows how to get the most out of this unicorn database that no one else really knows a lot about, then John's going to be the person that people come to for help with writing queries, with why isn't this working the right way, with why is this slow. And then John becomes a bottleneck for everyone else. So the complexity versus simplification trade-off is something for everybody to decide and consider on their own. For me, I prefer to introduce as little complexity into my technology stack as I can get away with, and even to shoehorn some databases into things that they're not particularly good at. For example, we are using MySQL for our time series backend in some ways that are not really relational database strength. But MySQL is pretty good at it, and we take advantage of some things like clustered indexes and so forth, and we get really good performance out of it. You might argue that we would be better off with a database that's specially built for time series, but I don't think that that's worth the complexity cost that we would pay, at least not at present. And I've put in a link here to a good thought leadership piece on the cost of complexity from some of the architects behind Yammer. The next category where we can potentially win some cost savings from databases is about consolidating multiple databases together and making sure that they're the right size. And I'm going to consider these two together because they often really go together. So consolidation, a lot of people are familiar with that because of the virtualization trend over the past decade or so. Virtualization is a way to drive greater utilization from servers. That's really the value that, there are other values as well, such as management and security and provisioning tools and so forth. But really what drove, in my view, virtualization as a trend was the consolidation of workloads to get better utilization out of hardware. That's what kind of drove the cost reduction for the bottom line for IT. And there might be a chance for you to consolidate if you can see an imbalance in the workload across similar servers. So let's say you have a heavily sharded database backend with lots of databases ostensibly doing the same thing. Different users are on different shards or something like that. And theoretically, they should all be very similar, but if the workload across them is imbalanced, then you probably have some that are underloaded and some that are overloaded, and you may be able to either right-size or consolidate some of those. And if you have underutilized server instances, then you may be able to pull some of those resources apart and share them across more database instances. Now, this can turn into quite the nightmare for management if you don't have the right tool chain for this, and obviously that's where things like Docker and its predecessors in virtualization and cloud computing have been coming from in the last decade or so. Looking at the same screenshot as before, but in this case, we're looking at the breakdown by host of this particular query. We can see that dbshard3 is over 85% of the time consumed by this query. And that's important because it means that dbshard3 compared to dbshard4 and dbshard8, which all run this same query, is very heavily imbalanced. So dbshard3 is getting the lion's share of that. And that might indicate that maybe we can consolidate those other shards into one, or that we should redistribute our shards. We'll take a look at that in just a second when we talk about capacity analysis. So to determine whether you can consolidate or resize instances, you need to check that there's capacity in all of the key resources. And it's very common for resources to be imbalanced in some way. There will be plenty of idle CPU, but you won't be able to drive any more CPU usage out of that server because there's no disk space, for example. Or you have more CPU and more disk space and so forth, but network traffic is already at its max. So that can be a delicate juggling game. And you also need to check the utilization of things like the buffer pool, or even things like the available connections limits in the database server, and make sure that you're not going to run out of something, some fixed size capacity limit, when you try and increase usage or consolidate things across more than one database instance. So I hypothesized that maybe dbshard 3 and 4 and 8 could be consolidated together in different ways. DB shard 4 and 8 were underutilized, and DB shard 3 looked like it was heavily utilized, right? So I took CPU utilization metrics off of those servers and just presented them here on the same slide with one another, and you can see that in fact we have a bursty workload as particular background jobs run, and during those bursty workloads we would actually not have enough capacity, CPU capacity alone, to run all of the workload on a single server. And from the CPU usage point of view, these servers don't look so imbalanced after all. So that's an illustration of how servers can look like there's an imbalance in one dimension, but in another dimension, you see that they're pretty well balanced. And really what you have to do is balance by the most constrained workload resource. There's another question. Even if you find that an instance is underutilized by all of the metrics and it really doesn't need to be separated to itself, how many servers or instances can you consolidate together? And this depends not only on the underlying hardware or virtual machine, but it also depends on the technology itself. In other words, MySQL or Postgres. The scalability concerns, particularly internal scalability around things like mutexes and other shared contention points. And you have to know the technology itself pretty well. So this is an area where if you're not competent to do this by yourself, it can really help to bring in a company like Percona, where they can help you with capacity planning and understanding exactly the meaning of all of these different metrics and how they can balance across each other. For example, I remember when I was at Percona, Vadim and I did some benchmarking and analysis on extremely high I/O capacity PCIe flash cards. And we found, to nobody's surprise, it was something that everybody was pretty well knew at that point in time, that MySQL was unable to drive as many I/O operations per second as those flash cards could sustain. And so we would run out of, actually we wouldn't run out of CPU, we would run into CPU bottlenecks around mutexes where we still had available resources when we tried to either increase the buffer pool size of those servers or we tried to push more throughput per second than they could sustain, and we were underutilizing various hardware. So it's kind of ugly, it's difficult to manage, but the way to do that would again be to break this thing into smaller pieces and co-locate a bunch of smaller pieces. Bin packing is a little bit easier to do when the pieces are smaller, and when they're not hitting those scalability limits where the diminishing returns comes very quickly, you can get much better per instance efficiency, and then when you add a whole bunch of instances together, you get much better overall efficiency. And that is still, as far as I know, in a white paper on Percona's website if you're interested in that. That's about the Virident flashcards. There's another concern or consideration here when you're thinking about what size your hardware should be, and that's really about the performance per dollar that you can get out of them. And that varies. This is something that's continually changing as newer models come out. What I have found in the past, just as very general guidance, is that the most recent release is rarely the most cost efficient in terms of price to performance ratio. It's usually kind of yesterday's or last year's model that has now become highly commoditized and is where you find the sweet spot in terms of, for example, dollars per gigabyte of RAM, dollars per gigahertz of processing power, all of those kinds of things. And then you have to balance those things as to how those systems can be assembled together. For example, if you find a sweet spot in terms of the memory chip size, and then you have to look at how many of those you can fit into a box and what is the cost of that box, and is that box also where you land in the sweet spot with regards to the CPU capacity and so forth. So this is a constantly changing landscape, and my advice to you, kind of generic, hope it's not too generic, I'm not trying to sidestep this question, but my advice is to, if you're purchasing your own hardware, stay up with the latest trends and just keep an eye on, probably every few months, take a look at, configure some price quotes on, for example, Dell and HP and a couple of other providers, Supermicro, et cetera, and see what you can get for your dollars. The last category that I wanted to look at, the opportunity for efficiency, is in using cloud computing. And I think this is a little bit less Kool-Aid drinking than there used to be, but I remember when cloud computing was really at the peak of the hype cycle, it seemed like you could just say cloud computing and everybody nodded their heads in agreement. Now, I think there's a little bit more nuanced understanding of that now than there was back in 2010. And I don't think anybody considers cloud computing to be just sort of washing your hands of the problem and making it someone else's problem. But that does actually play a part in this. You can look at this as, I'm renting the servers, I don't have to particularly buy for the long term. I can buy for the shorter term and optimize a little bit more locally. So there's a few particular areas where cloud computing might be a solution for you. One of the obvious ones is burstable capacity when load on the server is highly dynamic. Another is when you don't want to invest for the long term in all of your rack space and all of your servers and trying to figure out the lifetime of them and how to amortize cost over that lifetime. And then the final one is when your capacity needs are growing quickly and your procurement and racking cycle is potentially too long for that. The bigger vendors, if you're not one of the giant vendors, or even if you are one of the giant vendors, the cycle of getting new hardware, procuring it, and getting it installed is certainly longer than the 5 minutes or so that it can take to spin up a new computing instance in your favorite computing cloud. The cloud is not so much a cost efficiency driver for database workloads as it is a great way to waste a lot of money. And the three ways that I've found to waste the most money in the cloud are buying on demand instead of reserved instances. Now, I mentioned that one of the key use cases of the cloud is when you need burstable capacity. Burstable capacity doesn't really work for databases, and that's because data has inertia. You can't just provision a database server and then start using it. You have to get the data onto it, and that takes a bunch of time. And then you have to get it all warmed up, and that takes a bunch more time before it's sort of ready for a high-performance production workload. So spinning things up and down, and when you spin it down, you have to make sure that someone else somewhere else has a copy of that data and can serve it adequately. You can't, these are stateful beasts. You can't just shut them down and then turn them back on when you need them. And data has to be served from somewhere in the meantime. So really thinking about cloud computing as burstable capacity for data just doesn't work. It may work in some future magical universe where capacity is predicted and the data is moved around and multiple copies of the data are spun up and things are provisioned just as you need them. But I think that will be extremely magical indeed. So you should really view your database workload in the cloud as a steady, predictable, although maybe growing need instead of as something burstable from day to day or even week to week. So buying on demand just doesn't make a whole lot of sense. It makes a lot more economic sense. And in particular in the EC2 cloud where I have the most experience, buying reserved instances, whether you pay for them up front or pay for them as you go, committing to those reserved instances can save you a lot of money. And the payback period of those is typically in the 3 to 6 month range. Another common problem is buying the wrong instance type. You can do this with physical hardware as well. Of course, you can mismatch your CPU and I/O and memory and so forth. But it can be pretty easy to do in the cloud if you don't realize what's really behind these instances and the performance characteristics that are really behind them. So for example, a common one here would be buying non-provisioned I/O on EBS volumes. And then finally, my favorite way to waste money is by throwing hardware at the problem instead of trying to drive existing servers harder. And we run our poor little EC2 instances really ragged. My personal philosophy on this is buy smaller instances than we think we need and make ourselves go the extra mile to get more efficiency out of them as a way of making sure that we don't sort of get ourselves hooked on the all too easy to buy drug of more and more computing instances in AWS. So that's my personal philosophy, is artificially constrain yourself and force yourself to get the maximum out of those instances instead of just buying bigger ones. So how do you do that? And this is really where you can use workload characterization, some of the other tools that you can get with Vivid Cortex to derive a lot of efficiency out of your data. You're not going to improve anything that you can't measure, that's for sure. And the most important thing to measure in your database is the queries. That's the reason that they exist. That's why you've got them. You have these databases to run queries for you, and that is the #1 thing that you should be measuring. There's lots of other vanity metrics, such as cache hit ratios and so forth and so on. You should ignore those. Those are not metrics of performance. They're not metrics of resource utilization. What you should really focus on is queries. And so what you need to do is characterize the workload and then slice and dice it. Whether you do this with a tool like Vivid Cortex or our free query sniffing tools that you can download from our website, or whether you use, for example, slow query log analysis and tools like Percona's PT Query Digest or PG Fooing or PG Badger, whatever your favorite tool is, you need to analyze where the time goes, where the throughput goes, and where CPU, I/O, memory, those kinds of things go. And the way to do that is by gathering a chunk of workload data, query performance data from the server, ranking it by something that you want to optimize, such as total time spent in the database, and then you optimize the top ones. Now, you can use Amdahl's law to scan down through the list and figure out, I'll show you in just a moment, figure out which ones are not worth optimizing. And then you eliminate them if possible, because the best query is the one that you don't run at all. You reduce them if possible or combine them, such as reducing those n+1 query patterns to single queries. Or you improve the ones that you can't eliminate or reduce by indexing them better or rewriting parts of the application or so forth. And then you go back and do it again. And you repeat until you're done. In Vivid Cortex, Top Queries is the go-to solution for this. Top Queries is the tool. You know, Top Queries is really our #1 feature, and the vision for starting Vivid Cortex, in fact, all kind of revolved around Top Queries. So here I'm showing you on our own production backend, Top Queries ranked over the last hour by total time. This is the default view. And you can see that these first couple of queries, the blue bar goes about 1/3 of the way across on each of those. So taken together, those two queries represent 2/3 of the total time that all of these queries spend in the database, period. If you add up the top 3, that's the vast majority of all of the time spent in your database. Anything beyond that is going to be a marginal improvement in terms of reduction of load on the server overall. And that's what I was talking about Amdahl's law a moment ago. If you're trying to optimize query number 10, which might be, let's say, 1% of the total time consumed on this servers, then you can't expect to reduce the load or resource consumption on this server by more than about 1%. Whereas if we could improve those top couple of queries, we could potentially make a really significant difference for this server. And you'll notice that we have CPU and I/O columns on this display as well. Those are estimates derived from regression, and they match up pretty well with the time consumed bar in the leftmost column. But sometimes they don't. Sometimes you'll see that one of the queries that's a little bit further down the line is consuming or is credited with consuming the bulk of the CPU time or the bulk of the I/O operations or so forth. If that's the case, then even though that one may look like it doesn't cause a lot of time consumption in the server, it may be responsible for a lot of deferred background work. And you can look into that and see if you've got a background resource hog. So how much can you improve? Well, first of all, you can't improve it if you can't measure it. So that's where a tool like Vivid Cortex comes in, or slow query log analysis, or your tool of choice for figuring out where the workload is going on your servers. You do need per query metrics, no matter what you use. Global metrics are just not going to do anything for you. Going down that path with tuning scripts that you download from the internet, based on cache hit ratios or things like that, that is the path to de-optimizing servers and causing a lot of serious problems. If you do take a scientific approach to it with query measurement and systematically finding and improving the worst queries, you can, in some cases, we've been able to help people reduce 40, 50%, even more of their query workload. And I personally, in the past, not with Vivid Cortex, but in my consulting career, I've personally been able to reduce servers from 100% CPU utilization to almost idle. So you can drive tremendous improvement in systems by taking a disciplined approach to it. And there we have it. Getting close to the end of the hour, but this is a good time to wrap up and give you extra time for a cup of coffee. As a final note, I wanted to mention that really, although we talk and build tools for server optimization, they're really built for team optimization and IT optimization, because that's where the big wins come in. It's not about the queries being a little bit slow or the application being a little bit slow. It's really about what your database administrators spend their time doing, and conversely, what the developers spend their time doing. As I mentioned, the biggest opportunities are when you can free up a database administrator by offloading what they're doing, removing them as a bottleneck in IT's processes, and letting those 50 developers get their work done without having to wait for a database administrator to solve their problems while he's also trying to solve production outage or get the capacity planning done for the holiday seasons or whatever else. So it's really about empowering IT overall and not just about the server performance or server efficiency. So again, questions. I don't see any questions tweeted at me this time. And just to follow up, the recording will be on YouTube soon. And the slides will be on. Here's a couple of resources that you can find on our website. Various ebooks, my book, High Performance MySQL. And there's an upcoming webinar that Owen Zanzel will be presenting in August about breaking databases, and particularly about Ruby on Rails and the ORM and the bad things that can come out of that, and how to find and fix those things. So this looks like a good time to stop, and thank you all for coming. I hope this was good use of your time, and we'll see you next time.